Thank you. So I have to begin by saying the slides for this talk are on the web seminars page. There's quite a lot of them, but fear not, I'm only going to cover a fraction of them in the actual talk. This is a sort of pedestrian's guide to the presentation.
But it's been proven that in a 1-hour talk one could cover at least 100 slides.
An existence theorem, yes, however.
How long is that 1-hour talk?
The other thing to say to disappoint Alan is that this is just about the chromatic polynomial, so it's a univariate polynomial. Okay. I'm a univariate sort of person, and just to try to liven it up a bit, instead of using q, which is the variable that you've seen quite often, that variable which, when it's the number of colors, it's going to be called k, and when it's a complex variable, it's going to be called z. So, yeah, the initial stimulus came from Tutt's work on the golden roots and the silver roots and so forth, which I heard about in 1970. And for no particular reason, I, with some of my colleagues, looked at complex roots, and we found this family here, which are now called the cyclic ladders, perhaps call them the prisms. In other words, you take a rung, a K2, and you iterate it cyclically, and you get Ln. And we found by various means that the chromatic polynomial is what's written down at the bottom there. At the time, we also looked for the complex roots of these polynomials for the largest values of n we could do at that time, which wasn't very large, because this was the days of computing with Fortran and punched cards and so forth, and we got this picture. But at the time, we didn't understand what was happening at all. We didn't understand these curves. We didn't understand the form of the polynomial that we got. This was all sorted out in the ensuing years. First of all, the famous theorem of Baraha, Kahan, and Weiss that we've heard about many times, and in particular, Ron Reed and Gordon Royal wrote a paper in which they pointed out that this polynomial is precisely of the form to which the Baraha-Kahan-Weiss theorem applies. In other words, it's expressed as some polynomials times some polynomials raised to the power n, a sum of such terms. And so in this case, the polynomials raised to the power n are z squared minus 3z plus 3, and so on and so on. And there's actually one at the end, which you don't see because it's the polynomial 1, and that's raised to the power n, but it is there. And so the curves that we got are parts of the curves where those polynomials are equal in modulus. Those are the ones written down at the bottom. I've forgotten about the one with things equal to the polynomial 1, because in fact that doesn't play any part in the final presentation. So returned to this in 1999 and discovered that there was a lot of interesting work going on in other areas. So I decided to look at the simplest kind of construction, and that's what I'm just going to talk about today, no frills, where you just take a single base graph or component, which I call B. In the picture it's a path with 4 vertices, and some links, and you take n of these things and join them, and the links are the same every time. Of course, you can do variations on this. You can put twists in and so forth, and reductions of that kind are worth studying, but for the purposes of the talk, it's just going to be the simplest case. The key to solving this problem, or at least the key to analyzing the dependence upon n, which is the length of the chain in the physicist terms, is to notice that there's something called the transfer matrix, which is a 0, 1 matrix. I'll say more about it in a moment. And if we just take the trace of that matrix, the trace of the matrix raised to the power n, then that will actually give us the number of k colorings. K is the number of colors. And replacing k by complex variable z, because everything there as it stands was a polynomial, we get the formula of the form that's required for the Barak-Kahn-Weiss theorem. And so we're looking for places where the matrix T, which I've written as depending upon Z there, it depends upon K actually, K the number of colors initially, where these matrices have two eigenvalues with equal modulus.
Sorry, you're using a transfer matrix in which the size of the matrix depends explicitly on K, right?
That's exactly what I'm about to say, yes?
You're going to have to interpolate both the multiplicities and the eigenvalues with polynomials or algebraic functions.
What I'm going to say is, and what that next slide is an example of, is that we started off with this enormous matrix here of zeros and ones, and the size of the matrix depends upon K. In the case where it's the cyclic ladders, it's just the number of colorings of the base component graph, which is a K2, so it's K times K minus 1. And the entries in here are just zeros and ones. So that's not particularly promising from the point of view of analyzing what the eigenvalues are. However, what we're going to do is to reduce that matrix to its constituents, if you like, find invariant subspaces or whatever. Find invariant subspaces, and what we find when we do that is that there are some 1 by 1 matrices which just have entry k squared minus k plus 3. In fact, there's only one of those. Then there's a lot of 2 by 2 matrices. So I'm writing this matrix as if we reduced it to a diagonal form, or more or less that. And these matrices are the ones that's given there. In terms of k's, it would be 2 minus k, 1, and 2 minus k. And then the same things. And then there are k minus 1 of those. And then there are an awful lot of 1 by 1 matrices, which are just 1. And there are k squared minus 3k plus 1 of those.
I mean, this was a 0 and 1 matrix, so you're saying this is after you diagonalize it,
yeah,
you'll get these k dependent.
Precisely, yeah. So a similarity transformation or whatever, or finding the invariant subspaces, reduces it to this form. And this is good because the size of these sub-matrices are all fixed. They do not depend upon K. Okay? The numbers of them, what I call the global multiplicities of them, they depend upon K, and the entries of the matrices depend upon K, but the matrices themselves do not. So we can actually find their eigenvalues. So if I look at that second 2 by 2 matrix there, it's got eigenvalues 3 minus k and 1 minus k. And so when I take the trace, I get what I said before. So that is how the decomposition works in that very simple case. Another case which I'll come back to later on to show that we can do it without some of the hypotheses I've made. We take what I call the generalized dodecahedra, and here well, this is actually the picture we had before, isn't it? It's the path of length 4, and if I just took the case n equals 5, that's an ordinary dodecahedron, and so I call this the generalized dodecahedron. And by a similar analysis, you reduce it to, you reduce the chromatic polynomial, the trace of the big matrix, to this form where we've got three, in particular T0, T1 and T2 submatrices, and those are of fixed size. The first one is just a 3 by 3 matrix, second one's a 6 by 6 matrix, and the third one's a 4 by 4 matrix, in fact. So there's no great difficulty. I mean, 6 by 6 matrices aren't particularly nice, but they've got polynomial entries and you can do things with them. So this is just the preview. I'll come back to it later on. But using that reduction, I'm going to show you how you can find the curves, the limit curves, which the roots of that polynomial I just showed you approach as n approaches infinity. And I'm going to explain the various curious features of this picture, in fact, the triple points. So we can see that's what I mean by a triple point there. It looks like a singularity, but in fact, it's not a singularity in the technical sense. So this is what we're going to do. First of all, this business of algebra that I had on the this decomposition here is that's algebra. I'm going to try and explain that a bit more and show that there is in fact a very nice formulation of that which links up with things that have been studied in other parts of mathematics. I'm then going to go on to talk about the equimodular curves. That's where the moduli of the eigenvalues are equal, and how you go from those to the limit curves. And then I'm going to study the topology of the curves, and then there's more bits and pieces as well, which almost certainly we shan't get to. Right, so the algebra of the bracelet colorings. Couple of papers there. As I say, it's all on the web, so you needn't scribble them down now, but what's on the web is just the outlines. What's actually in the papers, of course, is proofs. At least I hope they're proofs. Okay. So let's start with how we set up the transfer matrix for a bracelet in general. So I'm going to just have, for the sake of argument, complete graphs. These are the components. I think I've called it K little b there. And each pair of these is joined by some links, which I'm going to call L. And we repeat that and form the cycle. So the transfer matrix is then defined by the formula that's here. The 0, 1 matrix, the rows and columns are labeled by the colorings of the base graph, which is just a complete graph in this case. And if the two colorings are compatible, by which I mean if you color this one with the coloring alpha and this one with the coloring beta, then the whole graph with the links in it is properly colored. Technically that just means that this vertex here has a different color from the vertex to which it's joined over there. But then we get the transfer matrix that we're looking at. And the theorem that we've already quoted, here is the proof, which I suspect most people know. Simple bit of matrix algebra. The trace of that matrix, matrix raised to the power n, trace of, is the number of k colorings, or so, yes, the number of k colorings. Okay. Now the key to the algebraic analysis is a very elementary fact, which is that the names of the k colors aren't really important. In other words, you can permute them. So if I colored red, green, and blue, and then you said, well, I want green to be red and red to be blue and whatever, then you still have a coloring. Okay. And that tells us that the symmetric group acts upon these colorings in a particular way. And what I've written down on these 2 pages is the technicalities of how that works, and the key fact being the one at the bottom of this page, which is a lemma, which simply says that if I do this procedure here and then apply a permutation of the colorings to the alpha and beta, then I'll get another compatible pair of colorings. So I've written that as a matrix R of omega for any permutation omega is going to commute with the transfer matrix that we started with. Now, those who've done symmetric group representations will know a bit of this theory, which I'm just going to gloss over. But the outcome of it is that we can find the constituents, which are what I had for the very simple case at the beginning, in all these cases, and they correspond to representations of the symmetric group. And we know, it is known, symmetric representation theory, that the representations of the symmetric group correspond to partitions of integers. So the pi that occurs there, those blocks that I had, correspond to partitions. In that case, it was partitions of 2. So there weren't very many partitions to look at. We'll see a slightly more illuminating case in a moment. And here is all you might ever need to know as far as this subject is concerned about the representations of the symmetric group and their relationship to the partitions. You have a pi, a partition, which for me, I always put the 0 parts in. So if it's a partition of a number 5, there are going to be 5 parts, but some of them might be 0. The dimension of the representation is given by a formula, which is expressed there. And so, for example, if we're just representing S3, symmetric group on 3 objects, there are 3 representations corresponding to the 300 partition, the 210 partition, and the 111 partition. And the dimensions are given by that formula that's there. So this we'll just look at a little longer, because this is the sort of culmination of the theory, with all the bells and whistles have been finalized, and it says the following. For the case where the components of the bracelet are complete graphs, it says we're going to be able to write the chromatic polynomial as a sum of terms, and the terms are of the form a multiplicity m of pi, depending on the number of colors k, polynomial, times the trace, and this is a constituent matrix. So for the particular L and for each pi, and it's for each pi which is a partition of a number less than or equal to the number of vertices in the base graph. So that was my KB there. So pi has got to be a partition of any number up to b. We can write it in that form. And what's more, I can tell you an explicit formula in terms of the partition for the multiplicity. Clearly a polynomial from what's written down there. In fact, it factors completely over the integers into linear factors. The things we're really interested in, and which I'm not going to tell you how to do all the details, because it simply couldn't be done in the time available, is how you work out the constituents. But be assured it can be done. So these T matrices, which are the constituents, little ones I had before, we know their size. That depends upon the dimension of the representation pi, and their entries depend upon the number of colors. But they're polynomials in the number of colors, which is good. And yes, that's all we need to say. So let's see if we can find an example. Yes, here we go. So here the components are K3s. So we've made some progress from K2 to K3. Simple links, and the partitions of numbers up to 3. I can write down the multiplicities that I require in terms of the explicit formula that was on the previous slide. They come out like that. And what you're left to do is to find the constituents. Now, I have to say that when Robert Schrock and I first did this, we did it by different methods. Both of us did it by different methods. But we were very happy that our methods gave the same answer, but neither of those methods was actually the full strength of the theory that I've just shown you. I did it by a rather ad hoc method involving finding some essentially bases for these invariant subspaces, but without understanding quite why the theory worked. So here is the answer anyway, and you see that now we've got the polynomial expressed in levels, as I call them. So the 0 level, we always have to allow the partition 0 of 0, and that's just has multiplicity 1, and then there's a polynomial raised to the power n, and then let's just look at the second line, third line. So here is a partition of 2 into one part, one non-zero part. Here is its multiplicity according to the explicit formula, and here are two things raised to the power n, which are z minus 5 or k minus 5 and k minus 2. And so that means we've actually got a 3 by 3 matrix here. One of the eigenvalues is k minus 5 and the other is k minus 2, or two others are k minus 2. And the same for the others. The bottom line, lots of things have been rung together because all the eigenvalues turn out to be minus 1. And so we've added up their multiplicities and put it all in one term.
I don't understand why in the second, third, and fourth terms, inside the brackets, you get an eigenvalue to the n plus a 2.
Yeah,
there's another eigenvalue to the n. I thought that the brackets were trace of something.
They are, and they're the trace of a matrix which has the eigenvalue z minus 5 once and z minus 2 twice.
Okay.
Yeah, which is good. So it's a 3 by 3 matrix. And those are the...
Can I ask, why do you get representations of S1, S2, and S3? Why is it of this form?
Well, why is a difficult... the theory leads you to that decomposition. To go more deeply into it, I think you have to go to the papers and sort of read the theory.
Well, why do partitions of 2 and 1 also occur?
Well, let me tell you, when you construct the bases which lead to this representation, the bases are of the form, take a subset of the vertices and fix those colors. And so the subset that you fix the colors on can have sizes 0, 1, 2, or 3. And you take elements of the basis, which are essentially linear combinations of colorings for which the colors on this fixed set of vertices are given, and you apply the transfer matrix to that, and you show that various subspaces are invariant. And that was the ad hoc method we used first of all, and then it turned out that in fact a good way to get these bases was to use the theory of spec modules, which actually provide you with the actual representations that the symmetric group representation people do. You don't actually have to use their representation. If anything you write down that is a basis, and you calculate the action of the transfer matrix on it, you will get the answer. But if you use the spec module basis, then you get you see exactly why these numbers come out. That's why there was some ad hocery about the initial stages of this, because we did some calculations and we got lots of terms, and when we thought we got enough terms, we stopped. But now we know that there is a theory which guarantees that we're going to get all the terms by this method. Yes?
Now the sum of all the amplitudes at a given level is a Chebyshev polynomial, and you have somehow broken that up. So are you going to provide an explicit formula for what it is after this breaking up?
The explicit formula is on that page there, and what you're saying is that if we add those m pi of k's for pi a partition of a particular number, we're going to get a Chebyshev polynomial. Is that right?
Well, isn't that true?
I think it is, yes. So we're looking, for example, in the last line there, where because all the eigenvalue, all the matrices are the same, all the ones have been added up, and you're saying this is the Chebyshev polynomial in some sort of concealed form.
Right.
Yeah. Good. Okay, so what have we got here? Oh yes, that was for a particular set of links with base graph K3. If we chose a different set, then we get the same things in the red colours, the multiplicities, but we get different things in the eigenvalue terms. And that has to be worked out. And so that you don't ask me this, of course, the base graph doesn't have to be a complete graph, and what you do when it's not a complete graph is you have to break up the space of colorings into what actually look like complete graphs, which means that you look at the color classes. So for the path of length 4, there are 5 color classes, which I've just tried to indicate there, and you'd have to work with all of those individually and then do some adding up to get the answers. Okay.
You look at partitions of the vertices of the graph into one or more independent sets.
Yes, that's what I mean, a color class.
Kind of the shape of
yeah.
the colorings.
Yeah, yeah. And then when you've done that, an individual partition of the kind looks like a complete graph as far as colorings are concerned. Okay, so not bad. So now we're going to move on to the curves, and there's a paper on this, and also the research reports there which contain more sort of background material. So here's the story. We've decomposed the chromatic polynomial into this form, and from the Baraha-Kahan-Weiss theorem, we know that the limit points, the roots of the chromatic polynomial as n gets larger, are going to accumulate on these parts of the equimodular curves, and I've got to tell you what parts of means. So this obviously has to do with dominant eigenvalues, and we heard in parts of Svante Jansson's talk yesterday and in Robert's as well, this was discussed. So at any point there will be so many eigenvalues and one of them is going to be dominant. I have to say this is a simplified presentation. I'll tell you why in about 5 minutes' time. So we look at an equimodular curve where 2 eigenvalues, say lambda a and lambda b, are equal in modulus, and we'll call that, if we're looking at a part where we have a dominant eigenvalue, we'll say that's dominant. But there might be some other eigenvalue which is bigger in modulus than either of the ones that are defined by this curve. The Baraha-Kahan-Weiss theorem says that the only bits of the equimodular curves that we need look at are the ones where the eigenvalue is dominant, or the common modulus is dominant. Now, an obvious fact is that if we have 2 equimodular curves intersecting, so a lambda a is equal to a lambda b and a lambda a is equal to a lambda c, then the other equimodular curve you can form from the 3 is going to pass through that point of intersection. If at that point we're not talking about the dominant eigenvalue, that's irrelevant. But if we are, then we're going to get this kind of behavior that's in this little picture here, triple points. I call them triplet points, just to distinguish them from triple points, because they are not singularities of a curve. They are points where 3 curves intersect, and what happens is, as you can see there, that the bold ones are parts where the dominant eigenvalue changes. On this one it changes from A to B, but on this part here, let's go over here, where it changes from A to B, actually C was dominant, so we don't see that in the limit points of the polynomial. For an example, these are the ones I had a moment ago where we had K3, I'll call them toroidal since you've got a cycle going round one way round the torus and the n cycle going round the other way. These were all the eigenvalues that we found out of the matrices, and to work out all the equimodular curves, well, there's so many of them and you've got to look at each pair and so forth. But fortunately it turns out that they don't all play a part in the limit curves. In fact, very few of them do. And this is comforting also, this kind of example, because here we can actually work out the curves in xy coordinates, and we're pretty confident, although I have to say you can be led astray by Maple anyway, even with curves like this. If you ask Maple to do an implicit plot of this curve or similar curves, you can easily miss components of the curve, and you need to be on your guard all the time. So I'm just going to look first at the first three eigenvalues, which I do because those have some hope of being dominant, because it's a cubic and two quadratics, and there are the curves you get by equating two of those three in modulus. It turns out that there are no intersections. The second curve with those three branches lies neatly inside the first one, and the third curve, the BC curve, is actually outside the first one. And so C, or lambda C, actually plays no part in the limit points. The only thing that matters is the AB curve, and if you're inside the AB curve, then B is dominant, and if you're outside, then A is dominant, lambda A and lambda B. Now that's unfortunately not the end of the story, because there are a lot of other eigenvalues. So if we put in D, and I just do this one with hindsight because I happen to know this is the one that matters, okay? Then when we work out the curves, we've got the same, first of all, the same AB curve, but the AD curve and the AB curve intersect at these 2 points, and so we know that the BD curve will also go through those points. And so we superimpose those three curves, we look at the triplet point, those 2 points, and do the obvious thing as I had in my little diagram a moment ago, and you'll see there are the two triplet points. They're obviously complex conjugates, and as we approach the triplet point down here, that curve is dominant around there, but when we get to that point it changes over, and the rest of that curve, which is that bit I'm trying to trace there, is not dominant, and so that doesn't play any part. And you can work out which of the three eigenvalues, lambda A is the dominant one in the infinite region, and as you cross these curves, either you change a subdominant pair or you change a dominant pair, and if it's a bold curve you're changing a dominant pair, and so you're changing the region in which one particular eigenvalue dominates. Okay, well, I said that was a sort of simplified version, and it was simplified because I referred to the eigenvalue lambda A of Z or whatever it is and gave it a name and assumed that that was meaningful. Well, of course, the problem is that although we know the matrix that we started with has polynomials for its entries, when we find the eigenvalues, there's no guarantee that they're going to be polynomial functions of Z. In fact, almost certainly they won't be. And that means that we're dealing with all kinds of mind-boggling things, and we can either start to try and think in terms of Riemann surfaces and so forth, or try and simplify the situation a little bit. So this is why we have to, well, this leads us anyway, I'm going to give you another most simple version of what you have to do. I do actually believe that a more sophisticated approach to this might well prove fruitful, but let's just stick to the simplified one first of all. So we look at the characteristic polynomial of the matrix. And remember, the matrix has got polynomial entries, so the characteristic polynomial will have polynomial coefficients, the a1 of z, so forth. There will be polynomials. Okay? And what we're looking for are points where this polynomial has eigenvalues, has two roots with equal modulus. Now, the simple idea here is due to Salas and Sokal, and it simply says if two things are equal in modulus, then one of them is a multiple of the other, and the multiple is a number of modulus 1, S here. In other words, we're looking for a situation where the characteristic polynomial has two roots. Well, we're now looking for the characteristic polynomial, and the same polynomial with lambda replaced by S lambda has a common root with that polynomial. And we can do that by classical algebra by looking at the resultant of the two equations. So if we had a cubic, so a 3 by 3 matrix, characteristic polynomial degree 3, the resultant matrix, we did see this in another talk earlier on. It was, I think, in your talk. But there he had columns rather than I put them in rows. So you just have the coefficients of the first one, A1, A2, A3, and then you have the 3 rows of coefficients of the second one, S cubed, S squared, A1, S, A2, A3, and so forth. And the determinant of that has got to vanish. Now you can see there's a lot of structure there. So the determinant sort of has lots of factors. In fact, has S minus 1 to the factor m, where m is the size. M was 3 in that example. And the rest of it that matters is actually a reciprocal polynomial, which just means replacing S by S inverse doesn't make any difference. And so it turns out to be useful, or I find it useful, to replace the S, the complex variable of modulus 1, by a real variable given by that formula. T is S plus S inverse plus 2, so that as S goes round the unit circle, T goes along the real line from 0 to 4. And so we've got a real parameter now for these curves. And the theory tells us, theory of the resultant, we'll work out the resultant for a 3 by 3 case there, put it in terms of this T variable, and we get that. That's the generic form for A1, A2, A3 being indeterminates for a cubic polynomial. In a particular case, we'll be given a matrix big A, and the coefficients of the characteristic polynomial of the matrix will be just polynomials in Z. So the AIs are now polynomial functions of Z, and we bung those into the expression we had a moment ago, and we're going to get a polynomial which is polynomial both in T, the variable I introduced to represent the relationship between the two eigenvalues which have equal modulus, and the Z, which is the original variable. So a polynomial in 2 variables, and the nice thing is that we know that has, I say if and only if, and I think that's right, if and only if that polynomial vanishes, does the matrix A have 2 equal eigenvalues. Right, so that's sort of classical theory applied to finding equimodular curves of a general matrix without assuming that the eigenvalues are polynomials. So I don't have to have the kind of nice reduction that I talked about earlier on. So what this polynomial tells us, roughly speaking, is that if we apply the implicit function theorem, it's one reason for choosing the T variable in this way, it makes it clearer what's going on. We're actually just going to have a curve, and as T goes from 0 to 4, we're going to trace out a bit of a curve in the complex plane. And you need to know, my notation is that this round blob is the point corresponding to T equals 0, and the square blob is the point corresponding to t equals 4. Okay, so of course there's going to be more than one of these little threads that I've pictured there, and that's what we're about to investigate, how they fit together, because they form the equimodular curves. So the V polynomial, the one which gives us the criterion, started off as being a polynomial in T which had coefficients which were polynomials in Z. If we turn it round and write it as a polynomial in Z which has coefficients in T, we've still got polynomial coefficients. And the useful fact, which is a very simple lemma, is just the Cauchy-Riemann equations, that if we look at the mapping of the complex plane defined by, for a fixed t, by z goes to VA of t and z, then the Jacobian of that, which tells us when there are singularities, is actually just the discriminant in algebraic terms of that equation.
If you take, considering this as a mapping of z to something for fixed t, then it's a function of one variable, so Jacobian just means derivative.
Well, I actually mean the Jacobian taken as a mapping from R2 to R2 because I want the z to be an x plus iy.
Oh, you mean Jacobian in that sense.
Yeah. So I'm looking for places where that mapping from R2 to itself might be singular.
But isn't that, by the Cauchy-Riemann equations, isn't that just related directly to the complex derivative?
Absolutely, yeah. I mean, I said Cauchy-Riemann equation, but I write it in this form because it shows you that the discriminant of the polynomial, which tells you when you have double roots and so forth, is the same thing as the function that tells you when you have singularities, as we'll see in a moment. Okay, that's what I've just said. So what actually happens is that turns out that all the roots corresponding to t equals 0 are double roots. And so these threads that I showed you link up in pairs, and we get little segments, I usually call them now, like that. And you can think of that as going back to, remember we started off with a variable of modulus 1, so going round the circle, but the point is that the endpoints, the t equals 4 endpoints, don't have to be the same. And that, think of that in various ways. Partly, one way of saying it is because the transformation from s to t is singular at the origin. This accounts for, this is one way of thinking about the basic reasons why we get end points in the limit curves, the equimodular curves. They can also, of course, be the fact that the t equals 4 points can be double points of that equation. And I'm going to show you some explicit examples in a moment just to make it absolutely clear. And so you might have several of these things linking up in this way and forming a closed curve. And then the last point is that if we can find a root of the Jacobian or discriminant between 0 and 4, that's actually going to give you a singularity of the curves.
I'm sorry, what do you mean by singularity there?
This would mean
the curve intersects itself.
Yeah, and it would mean that there is a double root at t star of the polynomial that I showed you a few minutes ago. A double root because the curve crosses itself. So as we go from, I can actually point without a pointer here. As we go from t equals 4, there's a value of t here which might be 3.5, and we go to t equals 0, and we come back again, and a different value of t here gives us the same point. Okay. Now I'm going to very quickly just do some 2-by-2 examples. These are artificial examples. They're not chromatic polynomials as such, but the point of doing them is that the only calculations involved here are quadratic equations, and we can all do that, so there's no, no question that what I'm going to tell you is right. There are no artifacts of root finding procedures or algorithms involved. So look at this one, where it's 2 by 2 matrix at the top, written down explicitly. The V polynomial, the J polynomial, the Jacobian. The standard calculations I explained show you that we actually get the point corresponding to t equals 0. The double point is at z equals 0, and the 2 points corresponding to t equals 4 are at the real numbers -2 plus or minus root 6. And here is the curve you get. Nothing could be simpler. So the one t equals 4 point at -2 minus root 6, and another one at -2 plus root 6, and the double point at t equals 0. And we are absolutely sure that this is true because, in fact, by elementary calculus of quadratics, the equation has 2 complex conjugate roots at that point, and so complex conjugate roots have equal modulus, etc. That's okay. However, here's another example where I've changed what was, I think, -1 in the previous one to a +1. And now things look more complicated. Do the elementary algebra again. We get the double point t equals 0 corresponding to z equals 0. We get 2 separate endpoints, but we also get a singularity. And the singularity, notice this is a singularity which lies between 0 and 4. So it is a, say real is not the right word, but it's actually, it's in the range of t that we are concerned about. Okay, it's at 18 over 5. And it corresponds to the point z equals 1 twice. Okay. It just occurs to me I said something slightly wrong when I was talking to you a moment ago. But I will not, I think, confuse the issue by going back to that. Tell you.
So again, well, let me ask the question again to give you another chance to misstate it. T equals 18/5 is a point where, when you follow this arc, right? This arc is z as a function of t.
Yep.
That arc itself fails to be real analytic.
Absolutely.
So it's some kind of a cusp.
Well, you will see the picture in a moment. That's the information I've told you so far. The squares, remember, are the points where t equals 4. The round blob is the point where t equals 0. And the tensor product sign is where there's a singularity. Okay? We worked out the corresponding value of z. They all turned out to be real again here.
And the singularity is like a square root branch point or something.
Well, it's not entirely clear from that picture how you're going to put these little threads in there and join them up so that you get that, that situation. But I think because time will press, I won't leave you to think about it any longer. That's what happens. So the way I think of it, t equals 4 is here. You're now decreasing till you get to the singularity, which was 18 over 5, wasn't it? What's that, 3.6 or something? Yeah. Now you've got a singularity. And the curve, well, one way of thinking of it is that the curve continues around there to 0, comes back around here, and then zooms off back to t equals 4 again. So the elements of the curve that I showed you before finish up like that. And I like that example because I think it really does show, in terms that anybody can work out if you can do quadratic equations, what's going on. So just a couple of, by making similar changes, in fact, you could do a lovely animation of this if you wanted to, slightly beyond my technological capabilities, but the part that went along the real axis will disappear if you go to 2z plus 2. So all I'm doing in these examples is changing that element of the matrix. And that gives you a nice closed curve, and that's actually quite useful because there's a general theorem that says that's going to happen. If your big matrix decomposes in that form and you equate an eigenvalue of u to an eigenvalue of w for the equimodular curve, then that's going to be a closed curve, and that can be proved. So in that particular case, there were just two eigenvalues. The whole thing, the eigenvalues turned out to be polynomials, and so you could diagonalize that matrix I had a moment ago. Exactly. Okay, and then if I change the parameter to +3 there, we get the more characteristic picture where you've got the two endpoints and the double point at naught. Again, can all be calculated. Okay. Those were artificial. So here's a real life example. I showed you at the very beginning the generalized dodecahedron and told you that due partly to the work of Dr. Chang, who's here, the polynomial could be written in that form. Now that's going to be quite complicated when you start trying to work out all the equimodular curves and find out which ones are dominant and so forth. So I'm just going to tell you what happens if you look just at the very first part, the eigenvalues of the T0 matrix, which is a 3 by 3 matrix. And for that you can work out the coefficients of the characteristic polynomial. I've replaced z by z minus 2 to make them simple. You can do the v polynomial, which I had, and the j polynomial. The v polynomial is a polynomial of degree 16, and there it's written as a polynomial in z with coefficients, which are polynomials in t. All the 0 points, as I call them, are double roots, and some of the t equals 4 points are double roots. And so the thing, the curves, just for that particular part, are going to consist of 16 arcs joined up in 8 pairs like that. And we've got to lay them onto the complex plane so that the round blobs are at those points there and the square blobs are at the corresponding points. Some of the square blobs are, 3 of them, I said, are double points, and so the ends of the segments link up there. And it's also true that there might be some singularities, and here we can work it out. And this is the one point where we do actually solve a rather larger equation. An equation of degree 48 gives us some 2 values of t which are singularities, corresponding values of z are there. And those are the curves you get. So that's what, if I joined up that mess of points I had before with the equimodular curves, we actually get 3 components. You get 2 singularities there and there, and you get, well, you can see how it goes. Actually, when you go over to the full story, there are 2 other matrices here, and then you've got to look at the relationships of the eigenvalues between those 3 matrices. Most parts of those curves disappear. In fact, the final curves turn out to be closed curves, the ones that actually dominate in the full story. Okay. So, just to show you, well, I hope I've shown you already, but just to emphasize that this is not a subject which is properly understood, or at least certainly not properly understood by me. I'm going to talk about a very simple case and tell you all the things I would like to know about it, but I don't. So we had this situation beginning of complete graphs. So that's a K3, but it could be of arbitrary size. It's going to be of arbitrary size. And the links are just going to be the identical links, if you like. So the simplest possible links you could have. Now, what we'd all like to know is not just what happens as the length, the n, increases, but what happens as the width increases. The r, or the, yes, I think it's become r now, it has, yes, as the r increases. Or possibly what happens as the n and the r increase together, but in a fixed ratio. That would be the physical question. So what do we know about this situation? Well, the good thing is that the formula I had at the beginning, the decomposition into terms of depending upon the partitions, works, and some of the terms can be worked out explicitly for a general value of r. That's the, oops, gone too far. Well, okay, let's just, that's the formula. Carry on. My conjecture is that all the constituent matrices in that situation, this particular situation, turn out to be eigenvalues, turn out to be polynomials. So you've got these matrices whose entries are polynomials, you want the eigenvalues to be polynomial. And it seems, calculations have been done for values of r, 4, 5, 6, that in fact that is the case. But I have no idea how that could be proved. So this is the main conjecture of this part, that if we take that particular situation, we're always going to get polynomials for the eigenvalue.
Could you say again, what is the structure?
The structure is just a complete graph. In the picture it's K3, but in general it's KR, and the links are direct links, the simplest. You can have multiple links. Well, we had a picture in there. Okay. So here are a few things. We usually call the terms where the partition is a partition of 0 as level 0, then level 1, and so forth. And we can work out these matrices in certain cases. There is always, at each level, the partition which has one part, and that's what group theorists would call the principal representation of the symmetric group. And there's the partition in which all the parts are equal to 1, and that's what the group theorists would call the alternating representation. You can work out the sizes, and it turns out, as I say there, that I can actually give you explicit formulas for the matrices and their eigenvalues for those two representations. But once we move on beyond that, we run into difficulty. At level 3, there's a partition of 3 into two parts, two non-zero parts, 2 and 1, and I don't know what the eigenvalues of that, the corresponding matrix are. It's and again, the size depends upon r here. The r, the width is increasing. That's where you have to think of a change in your sort of mindset. I think there are only 4 distinct eigenvalues, and if the main conjecture is correct, they will be polynomials of degree r minus 3. But I can't tell you what they are, and I can't prove that conjecture. For smaller values of r, less than 5, for example, some of them disappear because things collapse when you have small values. And I don't have any conjecture for the multiplicities there. So here is just actually what we do know at each level for 2 particular partitions. Partition with 1 part and the partition with L parts, all equal to 1. I can actually give you formulae. I've just written down the names for the eigenvalues there, but I can actually give you formulae, and they're in the paper that I referred to in the earlier on. So there are going to be that number m, which is the minimum of L and R minus L for the principal representation, and there are just 2 for the alternating representation, and I know their multiplicities, so forth. So that's quite interesting, but it doesn't seem to generalize. If we go to nearly the bottom level, where we have level r minus 1, so a partition of r minus 1. Okay, now, of course we've got to think now r can be large, there can be numerous partitions of r minus 1. Conjecture is that the eigenvalues of all these matrices are the simplest linear are linear polynomials, so just z minus something, in fact z minus something, where the something is between 1 and 2r minus 1. We know that the principal and alternating representations contribute, both of them, 2 terms, although each of them contributes 2 terms of that form. But Why it should work out that all the partitions contribute terms of that form, I have no idea, except that that seems to be true for the few values that have been calculated. And then there's an even more sort of algebraic conjecture, which probably is based only on the evidence of the two lines above it there, that the representation corresponding to a conjugate partition and the partition itself, they're linear terms where the I and the I star are related in this very simple way. Again, I have no idea why that should be true, and I should very much like to know why. The bottom level, where we have partitions of R, is actually easy because everything collapses to a 1 by 1 matrix, which is either 1 or -1, and so we saw that in the example. We know what all the eigenvalues are. I made an attempt 2 or 3 years ago to get a bit further with this, and I think it's fair to say I did get a bit further, but it wasn't far enough to make it anything publishable. But if anybody is keen enough to work on this, I would recommend not having to do all the work that's in this research report before you start. Okay. Well, I've overrun, as is customary, and so we're not going to do any more work in progress. I think I'll finish there. Thank you. Questions?
If there were polynomial, all these eigenvalues, would it have some consequence other than that you can more easily draw the curves?
It would give you a very good start on saying what the limit curves are like as R tends to infinity as well as n tends to infinity. The limit curves of the limit curves. If that's, yeah. One of the conjectures which I think is in the bit that I didn't show you is that in fact the only things that really matter are the things that come out of the principal and alternating representations. I call that the wild conjecture. I think it's in the next part. So I've now said it alive. It's been recorded for all time. But if that were true, that would actually more or less settle what happens in the R tends to infinity limit, which I think is the hard problem.
So maybe you're saying that other representations of the symmetric group, apart from the alternating and the principal one, will not appear.
That's right.
That's what
Yeah, they appear, but in the limit, the eigenvalues that you get from those ones are dominated by the ones that I already know about.
In all of your cases, the limiting curves are bounded in the complex plane, and they have to be because your families of graphs have bounded maximum degree independent of the length.
I mean, they can go. There's an equimodular curve.
But a
BC.
subdominant part.
Yeah, a subdominant one. Yeah.
The dominant parts are bounded.
Yep.
And as I said, they have to be because these are graphs of bounded maximum degree. But in your transfer matrix formalism, you can probably see that, right? I mean, don't you, for each problem, don't you get one eigenvalue which behaves for large Z as a higher power of Z than the others, and therefore is
Yes.
inevitably dominant?
So in this example here, you've got the cubic eigenvalue. Yeah. But that's very obvious there because we're talking about, well, actually that one, yeah. If all the eigenvalues are polynomials, then that's probably very plain. But if they're not, then is it as obvious?
No, it's not, but it must come out, right? It must come out that, let's say you have a square root branch point, then maybe you'll get cubic polynomial plus or minus in Z, plus or minus square root of 6th degree polynomial
Yeah.
in Z, so that one of the signs is cubic. One of the, if you take, say, the plus sign, you get something that at large Z is cubic, and if you take the minus sign, the cubic part cancels and you get something that grows more slowly. So it'd be interesting to see in the transfer matrix formalism directly that happening.
Yes. I'm not sure that you can do a Perron-Frobenius type argument directly on the transfer matrix in
No,
general.
but maybe just looking at the degrees of the entries in your transfer matrix, maybe you will see that there's one entry, one diagonal entry, which is a higher degree polynomial than every other entry in the transfer matrix.
Yeah.
That's a setup that Jesus Salas and I find
Right.
in something like this with different boundary conditions.
I haven't got the matrix here. I've only got the characteristic polynomials. But in the papers that were mentioned, the matrix exists, and that would be a good place to start looking, because this is obviously a case which has the right level of complication to make it interesting without being totally impossible. Bill.
Is there a transfer matrix method for flow polynomials?
Well, I think there's a transfer matrix method for anything. Have people, I think we've heard it this week, the presentation that I've given, as I said, was a sort of presentation, pedestrian presentation, and I wanted actually to have objects there, the colours, and to have the colorings and so forth. But it would be good to do it for pots in general, or ZQ, Z of Q and little z, or Z of Q and vector V. And I would have thought either directly by taking the objects to be the flows and making a transfer matrix. We started off with this very big transfer matrix where the rows and columns corresponded to colorings. So maybe you could have the big transfer matrix where the rows and columns correspond to flows and make some direct definition. Or you could simply rely on the algebraic formalism and start off with the Q, whatever it is, being an integer, and doing something of that kind, and then carrying that over.
I mean, Schock, Salas, Jacobson, and other people have done the general Potts model directly in the Fortune-Castellane representation rather than in the coloring representation.
Yeah.
So you get everything explicitly as a polynomial in Q and V. So if you want, you can put in V equals -1 for chromatic, V equals -Q for flow. What would be interesting to know is we know that there were simplifications when you restrict to the chromatic polynomial because certain partitions don't appear. Are there simplifications when you restrict to V equals -Q? I don't know.
No, I don't
Maybe
know.
there's some specialization to the flow polynomial.
I mean, maybe I focused in my sort of questions and conjectures on things that specifically came out of this talk, but there are obviously much wider questions and conjectures which would be of great interest. And, yeah. Okay.